Let's now look at adding graphs together, also called superpositioning. I don't know if you've heard that term, superpositioning of graphs. If we want to add two graphs together, then it really is just a matter of adding the y-coordinates together. That's all we really need to do. So let's do x squared plus x. Now, of course, we know what this looks like, but let's do it by actually adding y equals x squared and y equals x. So how do I approach it? Well, the x and the y intercepts are usually easy to find. So I know, well, both of them go through the origin, so 0 plus 0 is 0. It's going to stay there. But there's also going to be one over there on the left, because whenever the same amount above and below, so that's what I'm basically looking for. And you can do that by sliding a ruler along or something like that. And when you get the same measurement above and below, then you know, oh, well, that's where the x-intercept would be. That should be it, I think, with that one. Okay. Then basically just draw yourself, and you don't have to physically draw. Again, you could just get your ruler and then have a look and measure it. But different perpendicular lines. So I'm going to put one there because the point of intersection is always a good one to plot. So I'll make sure there's a vertical line there. But however many you feel you need to complete the graph, I might have gone a little bit crazy. Okay. What I would then do, if I was doing this on paper, as I say, I would slide my ruler along and then I would see, oh, how many centimetres is it above? How many centimetres is it below? Do a subtraction. That's where I'll plot my point. So, boom, let's start doing it. There we go, look. And the shape emerges. And we can see it's another parabola. And then we join the points. And remember, it's not dot to dot. It's a smooth curve we draw. There we go. Let's try this one. X plus 1 on x. So it's not as immediately obvious what this one's going to look like. So there's y equals x, and there's y equals 1 on x. Okay. First point I've actually plotted in is at the point of intersection. So I know it's twice whatever that y value is. And I can do the same in the other quadrant. But then again, I'm just plotting points. So sliding points along. You'll notice I didn't draw any x-intercepts for this one, because it doesn't have any. The only x-intercept at this stage is the line y equals x, but I can't add that to anything because the other curve doesn't exist there. So the new curve's not going to exist there. And both are either positive or negative, so they're never going to add together to give 0. What ends up happening, if you look at it, it's sort of like this y equals x has ended up becoming the asymptote, which kind of makes sense. Because the other graph, as it's approaching infinity, the y value is approaching 0. So we're adding less and less to the line y equals x. So it becomes the asymptote when we draw it. Okay, things to keep in mind then when we're adding. Discontinuities. In either function, if there is a discontinuity in the domain, it will remain. It can't magically appear when you add it to something else. That makes this quite interesting if I add these two things together. So I've got x plus 1 on x, but I've also got 1 minus 1 on x. Now we add them together, we get y equals x plus 1. So the temptation is to draw y equals x plus 1. But x can't equal 0, because I can't substitute actually into either of them. I'm going to have a problem if I substitute in x equals 0. So whilst we think it's y equals x plus 1, we'll have a point discontinuity at x equals 0 for those two added together. That's next with the x-intercept. That's what I was talking about with when the y value is the same above and below the actual distance, then that's when you're going to get your x-intercept. Symmetry. Like functions will retain symmetry. So what do I mean by that? If you're adding two odd functions together, which is what we did up here with x plus 1 on x, they're both odd functions, then your new function should also be odd. And if you look at our red curve there, yeah, it is odd. But the same thing happens with even functions. If you add an even function with an even function, then the result should end up being an even function. Add an odd with an even, nah, your symmetry is going to be lost. Let's try this one. We're going to add these two absolute value curves together. The way of approaching this sort of one, I think, is to look at the critical points. And the critical points is, when do these absolute values become 0? So I'm going to look at what happens when x is less than negative 3. Now, if x is negative 3, and you can pick any number you like that's less than negative 3 to work this out. Give me a number less than negative 3. Oh, see, that's better. Everyone went negative 4. Next one, but no, you went 7. Yes, that's it. Negative 7. You sub that in, and you get absolute value of negative 4. So we want the answer 4, therefore we need the minus of x plus 3. Remember, it's either going to be, in this case, x plus 3 or minus x plus 3. And we ask the same question with 1 minus x. Which one are we going to use? 1 minus x or minus 1 minus x? So let's sub negative 7 into that. We get 1 minus minus 7, which is positive 8. So it's fine. I can leave that one with 1 minus x, which means when x is less than minus 3, I'm going to draw the line minus 2x minus 2. The next critical point would be at 1. So let's look in between minus 3 and 1. Pick a number between 1 and minus 3.
0.
Very good. That is the sensible choice in this case, because it's such an easy number to substitute in. So we sub it into x plus 3, we get 3. So we'll leave it as x plus 3. We sub it into 1 minus x, we get 1, so that's fine. We'll leave it as 1 minus x. So between minus 3 and 1, we're going to draw the line y equals 4. Now let's check the right-hand side of 1. Any number you like that's bigger than 1. 2, very good, okay, good. 2 plus 3 is 5, so we'll just have x plus 3. 1 minus 2 is negative 1, so we want the negative of 1 minus x. That one turns out to be 2x plus 2. So now we can draw our picture. So going up to negative 3, we're drawing y equals minus 2x minus 2. Then we have our horizontal line of 4. And finally, we have y equals 2x plus 2. So there's our two absolute value functions added together. Now, if you want to draw a subtraction, it really is the same thing as addition, because all you really got to do is add the negative function. It's probably an easier way of thinking about it. But anyway, let's have a look at this one. Y equals x minus sine x. So I've drawn those two in, but you'll notice I haven't drawn sine x, I've drawn minus sine x instead. X-intercepts, where are you? There's one at the origin, they're both 0, so that was easy. Any other x-intercepts? Oh, there's probably going to be some, are there? Somewhere along here, we're going to get the same above and below. You'll also notice these other points I've plotted in, because when one function is 0, then I know I'm going to be on the other one, because I'm subtracting 0. So I know I'm on those points. If I was to keep plotting, what I end up with, there we go. There's a few more points. Oh, why did I pick those points? That was at the amplitude of this curve. I thought that's probably a good one to plot, see where that ends up. So what you end up with is it's like a sine curve winding along the line, but notice the symmetry of it. It still has rotational symmetry there, but in between the two intercepts on y equals x, it's not symmetric. It's sort of stretched out a bit when it comes through. And if I had a bigger picture, you could see that pattern would keep going along y equals x. You get something like that. This is an interesting point up here in the box. If the graph is bounded by y equals a and y equals b, which the sine curve is, it's bounded by y equals 1 and y equals minus 1. This purple curve that I've drawn in should be bounded by x plus 1 and x minus 1. So if I was to actually draw those lines in, you'll find that there'll be tangents to those sine curves in there. All right, let's have a look at multiplication. So we're going to multiply two curves together now. Have a look at our y equals x e to the power of x. The x-intercepts are real important in this one, because that's when the new function is going to change sign. Because if one of them has an x-intercept, you're multiplying by 0. So that will become an x-intercept of the new function. Now for this one, we do have one, don't we? Because y equals x has an x-intercept there. So we know it's going to go through the origin, this particular one. Then what we do is have a look where it is. So I look at the signs, but I mean plus or minus. So on the left-hand side of that x-intercept, I've got one curve that's positive, one curve that's negative. So if I'm multiplying the values together, I should get positive times negative, which is, of course, so I should be down there. And then if I go on the other side of the x-intercept, I've got a positive times a positive, which is that goes there. So we've got a bit of an idea of where it goes. Y-intercept, well, in this case, it's already done because we know it's the origin. But that's, that's a good one to work out. Then, again, the value of 1 becomes important. Because if you multiply by 1, then it stays the same. So, for instance, there's the point 1, 1. So I know that's when this graph has a y value of 1. Therefore, the new graph, it must be on the other curve, because I've got 1 times whatever that y value is. And it'll stay at that y value. And a similar thing will happen at negative 1. Just got to be careful with the sign. But there's negative 1, negative 1. So when I multiply it, it won't actually go on the e to the x curve this time, because it'll be the negative of it. So it'll be a reflection in the axis. So it'll be somewhere like that. It'll be. What happens out at infinity and near the origin? Now in this case, near the origin is not a problem because we know it goes through the origin. But what's going to happen out at infinity? Because if we have a look at this right-hand side, theoretically I'm saying infinity times infinity. So there's a pretty strong chance the answer is going to be really big. But what is going to happen on the left-hand side? That one's going to 0. The other one's going to infinity. Multiply that together, what are you going to get? 0? Because you multiply by 0, you get 0. Or infinity. Multiply by infinity, you get infinity. Correct answer for this one is 0. Won't always be 0 though. Now, there's this idea called dominance. And it's about which curve dominates. Now, the one that dominates will be the one that gets steepest the quickest or shallowest the quickest. So when you're comparing y equals x to y equals e to the x, the exponential clearly gets steeper quicker. It also gets shallower quicker. So it will behave like the exponential. It's going to go towards 0 in this case. So that's how I knew that one. So that gives me now an idea of the shape. Okay, things to keep in mind. Discontinuities, once again, if there is a discontinuity, now there wasn't in our example, but if there was, it can't go in the new function, can't magically appear, that x value. Symmetry, again, symmetry will retain some form of symmetry. We'll get to that later. Let's draw this one. Now, we've seen ones like this before, and we've already looked at a way of doing it. This is a different way of thinking about it. You might prefer this way, you might prefer the other way. So y equals x squared, x plus 1, x minus 1 cubed. I've drawn all three of those in. We're multiplying those three things together. I'll mark in the x-intercepts. Anytime any of those have an x-intercept, the final answer must be 0, because we're multiplying by 0. So there's those 3 points. I'm now going to work out where it is. So I'll start at the very left. I've got positive times negative times negative. That would be positive. In between the next two, I've got positive times negative. That would be negative. In between the next two, I have positive times negative. That would be negative. Now that's telling me some information straight away. Because remember, we know at the origin it's going to hit there. So it must turn at that point in order to stay negative. Okay, next one, we've got positive times positive times positive, and we have positive. Now, bad choice of colour. I just put in what the actual one is. I promise you, let's get rid of the pic, there we go. I promise you that is not a straight line. It's just my very bad choice of scale. It actually turns at minus 0.00. So it's so close, it looks like it's a straight line there. But that actually is turning and then coming back up in that graph. Is that my preferred method for something like that? Nah, probably not. I probably prefer doing it the way we did before, where we go, right, there's our x-intercepts. The curve's going to behave like the power. So I know at 0, going to be like a parabola. At 1, it's like a cubic, and so on. I think I prefer that way. So not just one function times another. What happens if we square a graph? So multiply it by itself. Single roots will become double roots. So any single root will become a double root. Here's my random graph from the other day. Let's use this one again. So there's function x, we're going to square it. These single roots, and we know they're single roots because they're cutting like a straight line, they will become double roots. So they're still x-intercepts, but they now will become turning points rather than cutting through. Any stationary point will still be a stationary point. The y value may change, but at that particular x value. So here, this stationary point here, at that x value, well, the y value is going to square. Now it's above 1, so it'll end up going higher, whatever that one is. So up there somewhere. Got to be careful with these ones, because if we're squaring, it's going to go positive. So yes, this one, well, hang on, -1's down here. So when I square this one, it should become a smaller number, but it'll be on the other side of the x-axis now because it's going to be positive. So what do we know? We know we've got a turning point. We know it's up here. That's also going to turn. It's going to turn, turn, turn. What about this horizontal asymptote? Discontinuity is going to stay the same, but the horizontal and oblique asymptotes, square them. I mean, that's what we're doing in the function. We're squaring everything. So at the moment, I've got, well, it equals some constant number. So that's nice. I don't know, what is it, about a half maybe? Square a half, you'd get, so it's going to come down. The horizontal asymptote is going to come down. All right, now, if, and I'm just talking the magnitude here, that's why I put the absolute value. But if the magnitude of the curve is bigger than 1, then function x squared should be bigger than function x. So when you're drawing it, the new curve should be above the old curve because the y values are bigger. And the reverse will happen. So when it's below 1, the new curve should be below the old curve. Now the negatives, again, you've got a bit of an issue because it's going to reflect over. Well, 1 squared is 1, so that's a good one to plot in. -1 squared is 1 as well. So we'll plot that one in, and now I can draw it. Here, below 1, so the new curve is below the old curve. We cross at 1, and now the new curve is above the old one because we've gone above 1. But that same idea for each of these. We're going below, above, below, above, and so on. We also know we have to bend towards the asymptote. So after we come through this one, we must bend and go asymptotic to the horizontal asymptote there. Ooh, and there it is in all its glory. Isn't that lovely? Okay, division. Again, just like I did with subtraction, where I said, no, I'm thinking subtraction is adding the negative. I can do a similar thing with multiplication. So I'm saying, well, yeah, okay, I'm dividing by g, but what I'm really doing is multiplying function x by its reciprocal of gx. And so then all the same procedures can be followed, except now the x-intercepts of gx will become vertical asymptotes because they're now on the bottom of the fraction, and so they can't equal 0. So we know they're going to be, or maybe point discontinuities, but we certainly know it's not going to be in the domain. So let's do this one. X plus 1, x minus 2, on x plus 2, x minus 1. And yes, the other day we saw a different way of doing this, where remember we did polynomial division and got all that information. So here's just another way we could approach the problem. Okay, well, I'll have x-intercepts for the top of the fraction. So they're at -1 and 2. Bottom of the fraction will become vertical asymptotes. I can't have 0 on the bottom of the fraction. Now that's broken it up into regions. So the first one goes negative times negative times negative times negative, which is positive, and so on and so on. So I know the curve's going to be in all those regions. I can work out the y-intercept by just subbing in x equals 0. So I know y will equal 1. Now, what's happening? Again, you got that idea of dominance that might come into play. Or no, in this case, we've got 4 straight lines, so nothing's really going to dominate there. Find any asymptotes. So again, we could do our polynomial division like we did before. And we say, oh look, there's a horizontal asymptote at 1. So draw that one in. Is that enough information to draw our graph? So we're going to stay in this section up here, because we've got to bend towards the asymptotes. Haven't got any x-intercepts down here, so I can't cross over. But I know here I've got to go through this one. So I must start down the bottom, come up through the asymptote, go up, and then bend towards the other asymptote. And then on the right-hand side, we must have this sort of hyperbolic shape there. And I think this is the last one, but it's an interesting one. Sine x divided by x. Well, there's y equals x, and there's y equals sine x. So we're going to divide sine x by x. So all of those x-intercepts are x-intercepts, but of course At 0, it's not going to be an x-intercept. This one will actually be a point discontinuity. This limit, which we haven't really looked at yet, it's what's known as the small angle theorem. For very small values of x, the sine of the angle is equal to the angle. You don't believe it, try in your calculator. Go sine and put in a really small number, and you'll find that answer is very close to that small number. So we know that as we're approaching 0, sine x on x will be close to 1. So I'm actually going to have a point discontinuity at 1. Shade in the regions, it's still got that going up and down shape. But think about it logically, what are we doing? We're getting sine x and we're dividing it by bigger and bigger and bigger numbers. So this time, when we wind along the x-axis, it's going to get smaller and smaller and smaller. So we get something like that. There's a wind. I might have exaggerated it a bit, but it gets a bit smaller as we go along. Goes up to the point discontinuity there. We end up with an even function. How do I know that? Because sine x is an odd function, x is an odd function, and odd times odd will always give you an even function. Basically, if you've got the same type of function, multiply them together, you end up with an even function. So odd times odd will give you even times even will give you even, odd times even actually is odd there. So if they're different types of functions, they give you an odd function. Okay. Oh yeah.